And the mole concept is one of those things when students hear it for the first time, it's like that's kind of a bizarre word. It might bring to mind a little furry rodent. But the mole is a word that stands for quantity of items, just like when we use the word dozen, which stands for 12. So if we have 1 dozen of something, we have 12 items. And when we're dealing with a mole of something, turns out that we're dealing with 6.022 times 10 to the 23rd items. And this number also goes by a name. It's also referred to as Avogadro's number. And so, what I'd like to do here, this isn't really a right or wrong question, though there's going to be a right or wrong answer on it. If we go to the Socrative app, want to get some idea if you can guess how much or how big this number is. So we want to put it into perspective. So if I have 6.022 times 10 to the 23rd ping pong balls in a box, and I dumped it out, then the question is, what is your best guess of the space that would be taken up by that many ping pong balls? 5, 4, 3, 2, 1. And actually, surprisingly, it's enough to cover the entire Earth 60 miles deep in ping pong balls. And what's kind of odd about that is that when you look at a number like 6.022 times 10 to the 23rd, once we start writing these exponents on the power of 10, it's very easy to lose sight of how big those numbers are. Because, for example, if we talked about the number of people on this earth, and I forget exactly where we're at, does anybody know? Are we 7 billion now? Okay. So if we're over 7 billion, we'd write this number like this, which would be 7 times 10 to the 9th people. Okay, but if we just change it from 7 times 10 to the 9th to 7 times 10 to the 10th, there would be then 10 times that number of people. And if we put it times 10 to the 11th, there would then be 100 times that number of people. And so you can see here, once we start getting those exponents on there, these numbers really grow beyond what we might imagine them to be. And so these numbers here get to be really, really big. And one of the things that I like here is to even put this into perspective. If I had $1 mole, what I could do, I'd have some really deep pockets. If I started paying out $1 million each second, $1 million a second, I could give $1 million a second to every single person in the United States for about 60 years. And that would give me $1 mole. So then the next question is, do you think that we could fit a mole of anything in this room? And if we did, it would mean it would have to be really, really small, like made out of atoms. And it turns out that I do, and we're going to look at those in just a bit. First of these here is I have aluminum. And here's how we're going to write out these conversions. I have 1 mole of aluminum. And by the way, this is the correct abbreviation. I don't know why we leave the letter E off, but we do. So we say 1 mole of aluminum. This 1 mole of aluminum is equal to 26.98 grams of aluminum. And how many atoms are in here?
6.022 times 10 to the 23rd.
Right. And if we don't like saying that word all the time, we can use the word Avogadro's number. Exactly. Atoms of aluminum. And then I have here 1 mole of copper. And in this 1 mole of copper, we have 63.55 grams of copper. and it contains 6.022 times 10 to the 23rd atoms of copper. And I used to tell my students, and I still do, I think this number is so important you should have it tattooed on your forehead. And then one summer I had a student come in with Avogadro's number tattooed on their forehead, and I didn't know anything about henna at the time. Turns out it was a henna tattoo. But it panicked me because it stayed there for like, I don't know, a couple weeks. Okay? So, it was one of those Friday night things, I think, on a dare. Which brings us to the next question. See if you could figure out how we came up with those two numbers, and then ask yourself, what is the mass of 1 mole of lead? Help each other out, ask questions of your neighbor. See if you can figure it out. All right, we'll go 5, 4, 3, 2, 1. And the correct answer is 207.2. And where does that number come from? Yeah, more specific, right? This number right here, correct?
Yes.
Yep. So if you look at that number, what did we call that number before? Atomic mass, right. And so when we looked at the atomic mass, first of all, let's go ahead and write in the answer on here. We put in 207.2 grams of lead. And this is going to contain how many atoms? Right. Atoms of Pb. And again, we get that by looking at the atomic mass on the periodic table. But now we didn't measure this in units of grams before. Which units are these atomic masses given in? AMUs, right. So, and we call that value the atomic mass, and the units are atomic mass units. So we say that the atomic mass is 207.2 AMUs for lead. Okay? So now we see that the difference here is in the units. Now these values right here have a name. We refer to these as the molar mass. And the molar mass is the mass of 1 mole of atoms of that substance. And you'll see that they are numerically equal to the atomic mass, but we express the molar masses in units of grams. And the word mole has a Latin derivation which stands for heap or pile. So if we have a heap or pile of atoms, we have a mole, and so we're going to measure a heap or pile of them in units of grams. If we're talking about individual atoms, they're going to be measured in atomic mass units. Okay. Next up then, I have some molecular compounds. Here are a couple molecular compounds. Now I'm going to write some stuff down and we'll see what you can figure out. First one here, this is water. Here's the water. In the water, I have 6.022. No, I don't. What do I have? I have 1 mole. That's what I want to say. 1 mole of H2O. And in this mole of H2O, I have 18.02 grams of H2O. And in the other one here, I have 1 mole of methanol. And methanol has a formula of CH3OH. And this has a mass of 32.04 grams of CH3OH. Now, of course, if I have a mole of something, that means I have a number that's equal to 6.022 times 10 to the 23rd. But now we no longer label these as atoms, but we label them as molecules. So we'd have Avogadro's number of molecules of water, or Avogadro's number of molecules of methanol. And we call them molecules because if we look at something like water, let me put out a formula for methanol here really quick. This here represents a molecule of water. Molecule of water has 2 hydrogen atoms and 1 oxygen atom. This represents 2 molecules of water. And so in 1 mole of water we would have 6.022 times 10 to the 23rd of these. And this here is methanol as a formula of CH3OH. And so if I had a mole of that, then I would have Avogadro's number of these molecules. So then the next question would be, I have these 2 substances, and the 2 substances that I have here are sodium chloride, which is, of course, salt, and I don't have the other one here, but the other one I have is sucrose, which is also known as sugar. So I have 1 mole of each. 1 mole of sodium chloride and 1 mole of sucrose. And by the way, sucrose has a formula of C12H22O11. If you're thinking of C6H12O6, you're not thinking of sucrose, you are thinking of fructose or glucose. So now, I have those 2 substances in here. I have 1 mole of each substance. One of these is salt, one of these is sugar. Which one is the salt, do you think?
The one on your left. That one.
This one here? Why this one?
Because it's got fewer molecules.
Okay. We actually don't use the word molecules, and I'm not picking on you or anything.
Atoms.
Atoms, right. Atoms. This formula here has more atoms, so it's going to take up more space. So, my question to you, and there's 2 of them here now coming up. We call these values, and these are on the Socrative app, these values here we call the molar mass as well. So the next question on Socrative, the next 2, deal with the molar mass of sodium chloride and of the sucrose. So calculate the molar mass of NaCl. If you know how to do it, help a neighbor. If you don't, ask a neighbor. And then you're going to do the same thing for the sucrose. If you have it figured out, help each other out. Okay. We'll go 5, 4, 3, 2, 1. Correct answer is 58.44. And how do we get the 58.44?
You add up the masses on the table.
Right. And so we simply add together the 22.99 with 35.45.
And write it in grams.
All right, next up. Give your answer for the sucrose, the C12H22O11. Now see what you have to do. If you know what you're doing, again, offer your intellect to your neighbors. Put your head to work for somebody else. Because I can guarantee you there's some people in here that don't know what they're doing. 5, 4, 3, 2, 1. And the correct answer is with the majority here. It's 342.3. If you want the correct sig figs, 342.3. Now some of you took some extra digits along, but 342.3 is correct. So now to get that, of course, you need to add up all of the atomic weights. How many carbons are in the formula? 12. So we take 12 times the 12.01. How many hydrogens are in there? 22. So we add up 22 of those. And how many oxygens? 11 of those. So we simply multiply them out and then sum them together. Now as far as the terms go on there, there's going to be Avogadro's number of something of each one of these. And if we're dealing with sodium chloride, We're no longer dealing with a molecular compound. We're dealing with what type? Sodium chloride is it molecular or is it ionic? Do we remember now? Can our minds fried? How many think it's ionic? How many think it's molecular? How many still don't know? That's okay. All right, it is ionic. It is ionic because we have metals combined with nonmetals. And so if it's an ionic compound, we can't make molecules out of ions. But we can't put ions down as the correct answer here either, because if we have something like sodium chloride is made up of two different types of ions. They're made up of sodium ions, which are represented by the smaller spheres on here, and chloride ions, which are represented by the larger ones. And so there is actually no such thing as a molecule of sodium chloride. In an ionic compound, rather than talking about the number of atoms that are in a molecule, what we talk about is the ratio of the ions to each other. And so if you looked in a model like this, what is the ratio of the small spheres to the large ones? That ratio is 1 to 1. Actually, it's not quite that in this one because it's a 3 by 3 model. But it's 1 to 1. There's one sodium ion for every one chloride ion. And so in an ionic compound, that formula represents those ratios of the ions. And so the term we use for that is formula units. And so we say that it contains this many formula units of NaCl. Which then takes us down to our last one here on the Socrative app. And that is, if we want to put a word in here, we've now learned about molecules, formula units, and atoms. Then which choice should we put in there? 1 mole of sucrose contains Avogadro's number of. So atoms, molecules, formula units, or ions. Go 5, 4, 3, 2, 1. And it's molecules. It's molecular because all of the elements in here are nonmetals. So when we have bond nonmetals to nonmetals, we have molecular compounds. That's it for today, folks. See you later.